In this section, we will see how to use integrals to solve another interesting geometric problem. We will use integrals to find the area of surfaces formed by revolving curves about the x or the y-axes. Now let's think of a problem that we've considered previously. We've used integrals to find volumes of solids that were formed by rotating two-dimensional areas or two-dimensional regions about the x or the y-axes. And we even did other lines of rotation. We did horizontal and vertical lines. But recall that these sorts of problems looked something like this. We had some function, f of x, and we rotated that function around either the y-axis or around the x-axis or around another horizontal or some other vertical line, and we found a three-dimensional solid. So let's imagine what that solid might look like here. And for this example, let's just think of rotating around the x-axis. Might look something like this if we're integrating, say, from x equals a to x equals b. Then we're rotating this curve, and we get this three-dimensional looking solid. It's hard to visualize here in 2 dimensions, but we can imagine what this would look like being rotated about the x-axis. Now, we thought of this as a solid shape. We found the volume of the interior of this sort of shape. In this section, we want to find the surface area of these sorts of shapes. So rather than finding the volume of a mountain enclosed by this region, we're just going to think of the exterior of this region and try to figure out what is the surface area of that shape. Let's try to develop a formula for this, and let's think in terms of slicing up the surface area here, finding the surface area for a representative slice, and then using an integral to add up all of those representative surface areas. We've seen this sort of concept several times in previous sections, so let's apply that idea here. First of all, let's just think of a slice of the surface area. And what I'm going to do is think of a small portion of the curve right here, and I'm going to just think of spinning that portion of the curve about the x-axis. We'll just focus on rotations about the x-axis first. If I spin this small portion of the curve about the x-axis, I get a small band of area that looks something like this. So rotating this small piece of the curve around the x-axis gives us this circular band. Now, let's say that the length of this portion of the curve here is dl, just like we did for arc length. Let's think of that small length along the curve as dl, some small difference in the arc length. What we want is an expression that gives us the surface area of this slice of the figure. We would like to know how much surface area is there along the exterior of this band. Well, let's imagine this as a cylindrical shape, and let's think of a radius here. This is some radius in the y direction. We'll just call this y. So that's the radius of this band. And we want the surface area of the exterior of the band here. So imagine taking the circumference of this circle and then multiplying that circumference by the little bit of thickness that we have here. If we multiply the circumference by the thickness, that will give us the surface area of the exterior of the band. So let's write dA for a small bit of area. That's the surface area for this slice. If we can find the surface area for this slice, then we can integrate to find the total surface area. So dA represents the surface area of the slice, and we can find that once again by multiplying by the circumference of the slice times its little bit of thickness, dl. So once again, geometrically think of taking the circumference here, multiply the circumference by this thickness dl, and that will give us an approximation for the surface area of that band. So circumference is 2 times pi times the radius, 2 pi, and the radius here is this height, this y value. So we have 2 pi y times that length dl. That is an expression for the surface area of this representative band. Now, how do we find the total surface area? We find the total surface area by integrating, adding up all of these representative pieces. So we integrate 2 pi y dl. This ultimately will be a definite integral, and similar to arc length, we could integrate with respect to x or y. So we'll leave off the limits here because we don't know if there'll be x limits or y limits. But this expression is a general form for the surface area of the entire three-dimensional surface. So here we have the expression for the surface area of this graph rotated around the x-axis. Now, admittedly, this explanation is rather hand-wavy. We're really glossing over some details here. We're missing out on a couple steps that would really explain this more rigorously. But as far as an intuitive understanding of where this formula comes from, hopefully this explanation of this band and finding the area of the band, hopefully this makes a little bit of sense. Now, we could also think of rotating around the y-axis. If we rotate around the y-axis, we get a similar expression, except the radius would be a distance from the x-axis. So we'd use x as the radius in that case. So if we rotate around the y-axis, the formula is 2 pi x. It's the same except for the radius. Instead of having a y radius, distance from the x-axis, we have an x radius, which is the distance from the y-axis. So we have an expression for rotating around the x-axis or for rotating around the y-axis. These integrals will give us the surface area of the resulting shape. Now the dl for both of these expressions is the same dl that we saw when we did arc lengths. So dl here can have two different expressions. We can use either dl equals the square root of 1 plus dy dx squared dx, or the second option is the square root of 1 plus dx over dy squared dy. Once again, we saw these when we did arc length, and if we integrate with respect to x, we'd use this expression. Integrating with respect to y, we would use that expression. Now, we can use either expression for dl in either of these integrals. One integral is rotation about the x-axis, the other is rotation about the y-axis, and notice that this seems maybe a little bit backwards. We use a 2 pi y when we rotate about the x-axis, and we use a 2 pi x when we rotate about the y-axis. So this might seem a little bit backwards. We use y to rotate about the x-axis, we use x to rotate about the y-axis, and really it's helpful to think of y and x here as radii. So these two expressions give us rotation about the two different axes, and in both of these expressions, we could use either one of the dl expressions. We can integrate with respect to x or with respect to y. This is different from volumes. When we did volumes of rotation, rotating about a horizontal line like the x-axis required integrating with respect to x. Rotating about the vertical line like the y-axis, that was integrating with respect to y. Here, we can integrate with respect to x or with respect to y, regardless of whether we rotate about the x or y axes. So an important point is that the variable we integrate with respect to is independent of the axis that we're choosing to rotate around. We can choose either expression for dl, regardless of the axis of rotation. In fact, we could set up two different integrals, one integrating with respect to x, the other with respect to y, that would give us the same surface area rotated about either the x or y axis. Let's practice using these surface area formulas in some examples. Take a look at example 1. We want to set up an integral that describes the surface area of the solid formed by rotating the curve y equals x squared about the x-axis, and we want to go from x equals 2 to x equals 3. So first let's start by drawing a picture of this so we understand what we're doing here. And we'll look at a better visualization with some graphing software in just a little bit. But we're taking the curve y equals x squared, something like this, and we're going from x equals 2 to x equals 3. My scale is going to be a little bit off here, but this will help us to visualize what's going on. So from x equals 2 to x equals 3, we're taking the function y equals x squared, and we're rotating about the x-axis. So that will give us something that looks sort of like this. We have this three-dimensional surface, and we want to find the surface area of this shape. What is the surface area involved here? All right, now when we set up one of these surface area problems, we need to pay close attention to which axis we're rotating about. Here we rotate about the x-axis. So the very first step here, before we're worried about which variables we use or any of that stuff, the very first step is to write down the formula for rotating about the x-axis. So surface area rotated about the x-axis. Here's the formula. Surface area equals the integral of 2 pi y dl. Now this is correct. This is 2 pi y. We're thinking of y as a radius here. And so rotating about the x-axis, the integral is 2 pi y. Now, just because we have a y here doesn't mean that we must integrate with respect to y. We're told for this function that y equals x squared. So we could replace the y with x squared if it's more convenient to integrate with respect to x. It actually doesn't matter which variable we use, and we'll actually solve it both. We'll solve integrating with respect to x and with respect to y. So first, let's think of integrating with respect to x. So if we integrate with respect to x, we're going to use dl equals the square root 1 plus the derivative of y with respect to x squared dx. Now, y equals x squared. So this tells us that the derivative of y with respect to x is 2x. So I can substitute 2x for this dy dx, and I'll put this expression for dl into the integral. So this integral becomes the integral of 2 pi y. And we're integrating along the x-axis because we're integrating with respect to x. So let's use the limits of integration x equals 2 to x equals 3. So those are the appropriate limits here. And dl is the square root of 1 plus dy dx. We just found that dy dx is 2x. So we have 2x squared, integrating with respect to x. We have a bit of a problem here because we're integrating with respect to x, but we have a y. We can't mix the variables like this. I can't have x's and y's in the same integral. How do we fix this? Well, I'm told that y equals x squared. So I simply take the expression x squared and use that instead of y. So the final integral here to set up this problem is 2 pi times x squared times the square root of 1, and I'll just go ahead and square the 2x, so that's 4x squared dx. This integral describes the surface area of this three-dimensional solid. Let's go ahead and take a look at problem 2. Problem 2 asks us to resolve the same problem. We're still rotating about the x-axis, but we want to set up the integral with respect to y instead of with respect to x. So once again, we're not changing the axis of rotation. We are still rotating about the x-axis. And it doesn't actually matter which variable we choose to integrate with respect to. We can integrate with respect to x or y and have the same surface area, the same rotated shape. So let's solve example 2. Here's our picture once again. If we integrate with respect to y, we're going to use a different expression for dl. So let's go through those steps here. If we integrate with respect to y, let's just do this off to the side. The expression for dl is the square root of 1 plus dx over dy squared dy. Now, we keep the same initial expression for surface area. This formula is the surface area formula for rotating about the x-axis. Our axis of rotation is not changing. We're still considering the same exact surface area. So we start at the same place. We start by saying surface area for rotation about the x-axis is the integral of 2 pi y dl. And now the dl will be in terms of y. So to get this expression, we need dx over dy. We need to solve the original equation for x in terms of y and then integrate to get dx dy. So if y equals x squared, we can solve for x by taking the square root of both sides. X equals the square root of y. Normally we would do a plus and minus square root here, but x is always positive. So we don't need to worry about negative square roots because x always takes on positive values for this example. So we'll just choose x equals positive the square root of y. Now we need to find the derivative of x with respect to y to get dx dy. So we take the derivative of x with respect to y. That's the derivative with respect to y of the square root of y. This is y to the 1/2, so we could take the 1/2 out front. It's 1/2 times y to the negative 1/2, or we could write it a little bit nicer as 1 over 2 square root of y. This is simply the derivative of the square root function. We're just using y when we're typically using x. So here is dx dy. We will substitute that into the expression for dl, and then we'll have an integral with respect to y. So the surface area integral is 2 pi y, and now dl is the square root of 1 plus, and we just found that dx over dy is 1 over 2 square roots of y, integrating now with respect to y. We need limits of integration now. This should be a definite integral. The limits of integration are going to be y values. They are the y values of these points. The way that we can get the y values of these points is to plug the x values 2 and 3 into the function. So when x equals 2, the corresponding y value is going to be 2 squared, which is 4. Again, the scale's off a little bit here, but we get the picture. When x equals 3, we plug that into the function, we get y equals 3 squared, y equals 9. That's the upper limit in terms of y. So integrating with respect to y, we use the limits of integration from 4 to 9. Let's do one more step to simplify just a bit more. We have the integral from 4 to 9 of 2 pi y times the square root of 1 plus, and this expression here should be squared. If we square the 1 divided by 2 square root of y, 2 squared is 4, and the squaring undoes the square root. So we could write this as 1 over 4y dy. Now, look back at the integral that we used integrating with respect to x. We changed the y to be x squared because we wanted everything to be in terms of x. When we integrate with respect to y, we just leave the y alone. That just stays y. We don't have to change it because it matches the variable that we're integrating with respect to. So these two integrals are both describing the same surface area. They're both giving us the surface area of this curve rotated around the x-axis. Even though one integral is with respect to x and the other with respect to y, they are giving us the same rotated surface, rotated about the x-axis. If we were to evaluate these two integrals, they would give us the same number. And the number is about 208.1 approximately. So this is approximately the surface area for this shape, 208.1 square units. These are actually complex integrals to evaluate. We do not have the tools in order to solve these by hand. It's possible, but it would be quite complex, and we don't have the methods yet. So for this problem, we just are interested in setting these up and understanding that they're really giving us the same exact value because they're describing the same surface area, even though one integrates with respect to x and the other with respect to y. Now, this isn't the greatest picture here, so let's take a look at some graphing software so we can better visualize the surface area that we're dealing with here. So here we have the function y equals x squared, and we're interested in the portion of the curve from x equals 2 to x equals 3. There it is. Now we're revolving this portion of the curve about the x-axis. When we do that, here's the shape that we get. So we have this three-dimensional surface, and the integrals that we just set up give us the surface area of this three-dimensional shape.